Good morning to all. I'm here to present a topic on process concepts. So, regarding process, a process is an active entity, and a process is a program in execution. So, uh, we can differentiate what is a program and what is a process. A program is a passive entity, that is, we can't do anything inside the program. The program is a simple set of instructions inside the system, but process is an executing program. So any program which is in execution is defined as a process. So it is an active entity with program. PC represents program counter. It also includes information about process stack and data section. So the process stack, so the stack, inside the stack, uh, it is having some information about a return address, method parameters, and local variables. And inside the data section, the information about global variables are present. And uh, next comes the process states. So a process can be in any one of the states during its execution. So it may be from a new state, running state, waiting state, ready state, and terminated. So a process can change its state during its execution. So an initial process, whenever a process enter into a system, it enters into a new state, and after it is starting execution, it enters into a running state. And if it is waiting for some IO, or some time slice expired, means it is in wait state. After, so the suspend, so here the process is suspended, and after it getting all the resources, then it enters into a ready state. Then finally, uh, if its complete execution, means it enters into a terminated state, which means it finishes its execution. So this is a diagram for process states. So whenever a new process enters into a system, it enters into it represents a new state. So it is admitted into a system with the help of a ready queue. So uh, a, this circle represents a ready queue. So the process enters into your system first, uh, first finishes its execution. So we know the operation of the queue is first in, first out. So the first process enter into your system will execute it first. Then the scheduler in the sense, the scheduler will dispatch one by one to the running state. For example, so n number of process enters into a ready queue, means the scheduler will dispatch one by one to the uh, uh, running state. So during the running of the program, if any interrupt happens, means it again go to a ready state. And in the case of some IO event, so for suppose a program needs some IO device, or some any interrupt, or any event where it happens, means it enters into a ready queue. Again, after getting all the resources, it's in the process of sent to a running state. And and if it finishes execution, it is sending into terminated state. So these are all the 5 states inside the process. So new state, running state, new state, ready state, running state, waiting state, and terminated. So next comes process control block. So a process control block is otherwise known as PCB, or task control block. So each process has its own process control block. The process control block is having information about the entire process. So a process state, the state of a process, and program counter. So PC, program counter, represents the address of the next instruction to be executed. It contains the address of the next instruction what is to be executed. So and CPU registers, CPU scheduling information, memory management information, accounting information, and status information. So This diagram represents the PCB. So initially, so the pointer points the current process, and the process can be in any one of the states. So whatever the states of a process, here it represents the state of a process, and the process number and PC program counter, then the registers needed for the current process, and memory limits. So then the list of open files. So the PCB contains all the information about the process and its important information. Next, process scheduling. So scheduling represents the order in which the process needs to be executed. So, so the CPU will schedule which process is need to be executed next. So, so the concept of scheduling is to maximize the CPU utilization. Suppose if a process is waiting for some resource, it is waiting for a long time means so the CPU resource is getting wasted. So to maximize the utilization of CPU, the CPU has to schedule uh, the incoming process. So for that, three queues are managed by the CPU: job queue, ready queue, and device queue. So whenever a new process enters the system, it enters into a job queue, and the ready queue means so the process which are ready to execute will enters into a ready queue, and device queue represents the process which are waiting for an IO device will waiting in the device queue. So the diagram represents so the diagram represents so initially so from job queue the process enters into a ready queue, and the CPU will do so whether the process needs an IO request. If a process needs an IO request means it enters into an IO queue. Then it so after getting the IO devices, it again starts executing. If any time slice expired means the process will stops and it enters into a ready queue. Then if a process executes a fork command, so a fork command is used to create a child process. So if a process is executing a child process, when the child executes means this child process will enters into a ready queue and waiting for an interrupt. So in all the cases, so if the process in the ready queue will be dispatched to the CPU, and CPU will check whether a process needs an IO request or any time slice expired, or if it executes a fork command or any waiting for an interrupt. So in these cases, the process enters into a ready queue again. So next, process scheduler. So the scheduler will do the scheduling process. And the process migrates between the scheduling queues throughout its lifetime, because so there are three types of scheduler: long-term scheduler, short-term scheduler, and medium-term scheduler. Long-term scheduler represents a job scheduler because all the jobs are entered into your system, because n number of jobs can enter into your system. So these jobs will enter. Because it is a long-term process, so there the name represents long-term scheduler, and the entered jobs will be so suppose or some 10 or 15 jobs are entering into your system, which the CPU will schedule the jobs entered into a system. So because we can finite the number of jobs, so the number of jobs is finite inside the system after it enters into a system. So we can count, so that the name represents a short-term scheduler. And medium-term scheduler, it is a mix of these schedulers, and the diagram represents so so jobs from the job scheduler will enters into a ready queue, and and it is dispatched to the CPU with the help of short-term scheduler, and the short-term scheduler will do which process needs to be executed. So if it is waiting for an IO devices, it will wait in the IO waiting queues, and after getting the resources, that is input output resources, it again enters into a ready queue. So the ready queue represents this queue will maintain a list of processes that are ready to be executed. And finally, so the CPU will differentiate CPU bound process and IO bound process, because CPU bound process, the arrow comes in the left side, and the IO bound process in the sense the process which are waiting for an IO. And medium term scheduler, so see, so new process enters into a system. The medium term scheduler will schedule the process in the ready queue, and the process uh, the sh- uh, the process which is dispatched to the CPU, and CPU will CPU, if any process is needed for IO, or any process currently is not needed to execute, means it will swap out and suspend. So it will swap out and it is entered into a suspended block queue. Then whenever needed, it enters into a swap in. So whenever needed, it is swapped in into a ready queue. So so this diagram is an example for medium term scheduler. And what is swapping means, the process, so here swap in swap out uh, uh, takes place, because when a process, so a process needs to be executed means it should be in main memory. But if a process is not needed to execute at this time, means so no need of placing that process in the main memory. So if it is no need, means it can swap out. So whenever the need arises, that is whenever the process needs to be executed at current time, it is swapped in, which is the concept of swapping. And context switch, so the context switch represents switching the CPU to another process requires performing a state save. So which means context switching means a currently a running process, if an interrupt arises, means the currently running process will stop executing, uh, and then from resuming its execution after the interrupt resolves. So at this time, the process needs to save the contents of CPU registers in PC, and the context switching occurs only in kernel mode. Next, operations of a process. So what are the operations of a process? Means a process can be created. So process creation, process termination, process creation, process termination, and the types of process are cooperating process and independent process. So in process creation, so the creating process, that is uh, what process is creating a new process is known as parent process, and the newly produced process represents a child process. So the parent process and child process can execute concurrently, one after the another. And it can concurrently execute, and also it can execute one after the another. And the child process can be created by using fork system call. And process termination, the process is terminated whenever it finishes executing its final statement and asks OS to delete it by using exit system call. So a new process is created by using fork system call, and um, the currently running process um, is destroyed with the help of wait system call. If a process terminates, then all of its child process must also to be terminated, which is called cascading termination. That is, if a parent process terminates its execution, means if that parent process creates some another process, means it will terminate. Then the type of process represents cooperating process and independent process. Cooperating process means if a process can affect another process. Suppose if a currently running process can affect another process, means it represents a cooperating process, and independent process means it can't affect or affected by other process. Then interprocess communication. So the messages between the process represents the interprocess communication. So there are two models in the IPC: shared memory model and message passing model. Shared memory model is the memory is shared between the two process. For example, a producer consumer problem. The producer is produces information, consumer will consume or use the information. So to allow both the process running concurrently means we are introduced buffer. So the buffer available, so the buffer is used to fill the process produced by the producer with the help of a variable in, and it is emptied by the consumer with the help of a variable out. So the buffer size can be bounded or unbounded. So buffer is empty when in variable is equal to out variable. So the producer consumer problem represents the producer can produce this information which is stored inside the buffer, and consumer can consume information from the buffer. So when the buffer is full means in plus one mod buffer size is equal to out means the buffer is full, and when in is equal to out means the buffer is empty. And message passing system, so we can we can pass message with the help of direct communication or indirect communication. In direct communication, each process want to communicate must explicitly name the recipient or sender, that is A is the sender and B is the receiver. So the sender name and receiver name must be explicitly mentioned. So which is an example for direct communication. And the communication link is associated with exactly two process, that is who is the sender, who is the receiver. The receiver is shared by, that is the message is shared only by the sender and the receiver. And there are two ways of addressing, that is symmetric addressing and asymmetric addressing. So in symmetric addressing, send so send function is used to send a message. So A is the sender and MSG is the message. And in asymmetry, send A is a sender and MSG is a message. In symmetry, we can receive a message using receive function call, that is receive of B is the receiver, MSC is the message. That is MSC is a message sent from the sender A, received to the receiver B. And in the form of asymmetry, so A is the sender, MSC is a message sent from party A, and it is received with the help of ID, not the appropriate sender. So this is a difference between asymmetry and symmetry messages, way of addressing. Then in indirect communication, we can send, so M can be any sender, any receiver. That is, we can't know the who's a sender, who's a receiver. That is, we receive message from only from the mailbox. So MSG is the message, and the buffering capacity is zero capacity. The buffering capacity may be zero capacity, bounded capacity, or unbounded. Zero capacity means so the buffer is empty. That is, whatever we are producing, it is emptied. Then bounded means bounded finite size of the buffer. Unbounded means it is some infinite size. Then synchronization. So synchronization represents, so the sender process and receiving process will synchronize to send and receive the message. So blocking send, non-blocking send, blocking receive, non-blocking receive. Blocking send means if a receiver is not receiving the current message which is sent by the sender A. If suppose A is sending message which is not received by the receiver because there may be some time delay. So sender have to block its sending the messages again and again. So if it is sending again and again, means it will result in traffic. So blocking send and non-blocking send. So in the blocking receive means if so if a sender so is doesn't get some acknowledgement means, so the receiver will block the receiving of messages from a sender. Next comes CPU scheduling. So the CPU will schedule which process is next to be executed. That is the concept of CPU scheduling. So which is a mix of CPU and IO burst cycle. That is, CPU will do which process needs to be executed, and if IO devices is needed means it will enter into IO. So CPU burst cycle and IO burst cycle. Then two types of scheduling, that is preemptive scheduling and non-preemptive scheduling. So preemptive means if a process is running, if some other processes enter into a system means with less time than the currently running process, then it is a switch over to the next process, which means if a current process is executed, it needs some if a current process is executed with some burst time. If a new process enters means with the shortest CPU burst cycle, then the current process will switch over to the next process. But in the non-preemptive, it will not switch over to the next process. And the criteria for scheduling is CPU utilization. So, so CPU should be used when at all time the CPU should be busy. And throughput means the number of process completed per unit time. TAT means turnaround time, the time interval between the process submission and the process completion. Waiting time is sum of periods spent in the waiting queue. And response time means time it takes to start responding. So next comes a CPU scheduling algorithms. So the first come first served scheduling is the first scheduling algorithm. So here P1, P2, P3 of the process enters into a system with burst time 24, 3 and 3 seconds. So milliseconds. So the process enters in the order of P1, P2 and P3. So the burst time represents the time needed for the process to execute. For example, 24 milliseconds is the time needed for the process P1 to execute. So 3 milliseconds is the time needed for the process P2 to execute. 3 milliseconds is a time needed for the process P3 to execute. So we can represent the burst time with the help of some Gantt chart. So Gantt chart here, so in the rectangle in the form of the rectangular split ups, we can represent the running time of the process. So at the time of 0, the P1 process can enter into a system. So at the time of 24th millisecond, it can complete its execution. So so P1 completes its execution at 24 milliseconds. So when P2 needs 3 milliseconds to compute, so 24 plus 3, 27. And at the time of 27 only P2 finishes its execution, and next comes P3 process, and the P2 process will finish its execution at 27 milliseconds. So when 27 is added to 3, it is getting 30. So at the time of 30 only, all the 3 process it finishes its execution. So the average waiting time and turnaround time. So P1, P2, P3. So WT represents waiting time, TAT means turnaround time. So P1 process doesn't need any time because at the time of, so for the firstly entering process is P1. So it doesn't need any time to wait. So at the time of 0, P1 enter into a process and its turnaround time is 24, which means this. Next, P2 process enter into a system at 24 milliseconds and it finishes execution at 27 milliseconds. P3 process enter into a system at 27 milliseconds and it finishes execution at 30 milliseconds. So the average waiting time is 0 plus 24 plus 27 divided by total process, 3 process, 17 milliseconds, and average turnaround time is 24 plus 27 plus 30 divided by total number of process, 27 milliseconds. So in first come first served scheduling, so the process enter into a system first will executes first. Then shortest job first scheduling represents, so CPU is assigned to a process which has the smallest next CPU burst, which represents, so the here for example P1, P2, P3, P4 are the process enter into a system with burst time 6, 8, 7 and 3. So so these are the time needed for these process to execute. So we can represent in a Gantt chart, that is among 6, 8, 7, 3 burst time. 3 is the shortest time needed for the process P4 will execute. So P4 will first execute. So a CPU scheduler will dispatch P4 process to execute. So P4, so at the time of 0, the P4 process can enter and it will finishes at 3 milliseconds. Next come from 6, 8, 7. 6 is the smallest burst time. So 3 plus 6 represents 9. So for P3 process, 9 plus 7 represents 16. Next for P2, so last is the P2. So 16 plus 8 represents 24. So the waiting time and turnaround time means P1, P2, P3, P4. So so the waiting for time for the process P1 is the left side, that is 3, and for P2 is 16, and for P3 is 9, and for P3 it needs no time to wait, so 0. So turnaround time represents, so for P1 is 9, for P2 is 24, for P3 is 16, and for P4 is 3. Okay, next priority scheduling. So the process with the process with lesser I mean the process with highest priority will execute first. So whenever a process arrives at a ready queue, so its priority is compared with the priority of currently running process. For example, here P1, P2, P3, P4, P5 are the 5 process entering into a system with burst time 10, 1, 2, 1, 5, and its priorities are 3, 1, 4, 5, 2. So the first priority is assigned to a process P2. So the P2 enters into a system first. So at the time of 0, P2 enters into a system with its burst time 1, and the next priority comes P5. So P5 needs 5 seconds to execute, so 5 milliseconds. So 1 plus 5 represents 6. And for P1 priority is the next. So it needs 10 milliseconds. So 6 plus 10 represents 16. And for P3 process is the next priority. It needs 2 milliseconds. So 16 plus 2, 18. And the last process is it needs 1 millisecond. So 18 plus 1 represents 19. So waiting time and turnaround time. So P1 needs 6 milliseconds to wait and it finishes with 16. P2, it needs 0 time. It finishes execution at 1 milliseconds. P3, it needs to wait for 16 milliseconds and it finishes execution at 18 milliseconds. P4 represents, so it enters into a system, it needs to wait for 18 milliseconds and it finishes execution at 19 milliseconds. P5, it needs 1 millisecond to wait and 6 milliseconds to complete. So so based upon the priority of the process, the CPU scheduler will schedule the process with highest priority. Next, round robin scheduling. So this round robin scheduling will execute based upon the time quantum. For example, P1 process needs 24 milliseconds, P2 is 3, P3 is 3. So P2 process and P3 process, it needs 3, just a small burst time when compared to P1 process, which needs 24 milliseconds. So a time slice is needed. That is, suppose, so here we are fixed as 4 milliseconds. So at the time of 0, P1 enters into a system. At 4 millisecond, it switch over to P2. So it needs, so P2 needs 3 milliseconds. So 4 plus 3 means 7. Next, P3 process. So 7 plus 3 means 10. So, again, so P1 finishes only for 4 seconds. So remaining 20 seconds is there. So at the time of 10, P1, 10 plus 4, 14, and 14 plus 4, 18, 18 plus 4, 22, 22 plus 4, 26, 26 plus 4, 30. So based upon the time quantum, the process will switch over to the next process. So if the time quantum is finishes for P2, it will switch over to P3. And its average, so the Gantt chart, and the average waiting time and turnaround time is, so for P1, 0 minus 4 plus 10 minus 14 plus 14 minus 18 plus 18 minus 22 plus 22 minus 26 plus 26 minus 30. So the summation, the calculated value would be 6. So it needs, so for process, P1 process, it needs 6 milliseconds to wait to finish its execution, and it needs 30 milliseconds to complete its process. And for P4, sorry, P2, it needs 4 milliseconds to wait, and it needs 7 milliseconds to finish its execution. So P3 needs 7 milliseconds to wait, and it finishes execution at 10th millisecond. Next, multi-level queue scheduling. So here the separate queues for here that is it is maintaining some separate queues for each memory size, priority, and some properties of a process can be scheduled in some separate queues. Multi-level feedback scheduling. So here each queue, it will give some feedback about the process states. So how much CPU it is, how much CPU time it is getting, how much IO bound process it is related to the current process, such that it will give feedback information in the form of multi-level queue. Next comes real-time scheduling. So real-time scheduling represents the real-time games with the help of some deadline. It is happening. It is finishes execution with the help of deadline. That is, for example, video games. Within certain time, we need to finish that task. So these are all the concepts in operating system. So what is process, and what are the states of a process, and what are the process control block, otherwise known as task control block, which is the information regarding the process, and scheduling queue, job queue, ready queue, and device queue, and process scheduler, long-term scheduler, short-term scheduler, and medium-term scheduler, and the swapping, in context switching, and operations process creation and process termination, and cooperating process and independent process, and inter-process communication. The next, shared memory model and message passing model, and buffering, synchronization, and CPU scheduling, and scheduling algorithms, first come first served algorithm, shortest job first scheduling algorithm, priority scheduling algorithm, round robin scheduling algorithm, multi-level queue scheduling algorithm, multi-level feedback queue level scheduling algorithm, and the last comes real-time scheduling. Thank you.